Hello students, in this lecture we will see the seventh numerical based on nodal analysis. So the problem statement is find node voltages. But here if you observe that nodal voltages are mentioned, nodes are identified, only the reference node we have to mark. So we will consider this as a reference node. So at node A, three terminals are there and here we can apply KCL. So KCL at node A. Summation of outgoing current is equal to summation of incoming current. Three branches are connected to node A. Out of that, in one of the branch you have current source and that 1 ampere is incoming towards node A. So this is equal to 1. And the remaining two currents I can assume as outgoing. So the downward current I can write down as VA minus 0 because the voltage at the reference node is 0, VA minus 0 by 2 plus VA minus VB by 5. So LCM is 10 over here, I will multiply by 10, so I will have 5 VA plus 2 VA minus 2 VB is equal to 10. And in equation format I can write down this as 7 VA minus 2 VB. I know that there is VC also, so 0 VC is equal to 10 and this is my equation number 1. Now I will apply KCL at node B. So KCL at node B. Three branches are connected at node B and none of the branch contains the current source. So I can assume all the currents as outgoing. So while applying KCL at node B, summation of outgoing current is equal to summation of incoming current. So the leftward current can be written as VB minus VA by 5. The downward current is VB by 20. And the rightward current can be written as VB minus VC by 4. And no incoming current, so that is equal to 0. LCM over here is 20. So multiply throughout by 20, I will get 4 VB minus 4 VA plus VB plus 5 VB minus 5 VC is equal to 0. In equation format this can be written as minus 4 VA plus 10 VB minus 5 VC is equal to 0 and this is my equation number 2. Now what is the speciality of this numerical that we will see. When you try to apply KCL at node C, you can easily write down this current, but when you try to write down this current, what happens is when you are traveling from node C to reference node, you can write down VC plus 5, but there is no resistance along with this source. So the denominator you may assume as 0, but that is the problem. Here they say that the voltage source is present between the node and the reference node, then you can't apply KCL at node C. In such case, then how to obtain this variable or how to obtain one more equation. So whenever such situation is there, the situation goes like this. A voltage source is present between node and reference node. Only voltage source. Not even a single resistance is present over here. In that case, VC is nothing but minus 5 volt. Why minus 5? Because this negative sign is connected towards node C and positive is over here. So if you try to apply KVL, considering the voltage VC is measured with respect to reference node, you can go like this: VC plus 5 is equal to 0. That means VC is equal to minus 5. In equation format, this can be written as 0 VA plus 0 VB plus 1 VC is equal to minus 5. This is my equation number 3. If they would have reversed the polarity of 5 volt, that means positive is connected towards node C and negative is towards reference, then VC would have been plus 5 volt. But in this numerical, negative terminal of the voltage source or exclusive voltage source is connected toward node C, hence VC is equal to minus 5 volt. So you have to remember two things. First of all, you can't apply KCL to a node where there is only a voltage source present between the given node and the reference node. And the second thing, the value of this voltage can be easily calculated by looking at the polarity of this voltage source. If negative is connected towards that node, the value of that voltage at that node become negative, and we have to write down that value over here. So you can solve these three equations simultaneously using calculator, and VA turns out to be 0.806 volt, VB turns out to be minus 2.177 volt, and VC is minus 5 volt. So we have calculated all the nodal voltages in this numerical. Thank you.